Welcome. Now, previous class I have discussed the stereochemistry, means how to tackle that if in a molecule stereochemistry is mentioned. On that case, how you tackle the problems. If the reagent is lithium aluminum hydrides or any other nucleophile reagents or any reagents are there, and if stereochemistry in the molecules is mentioned, on that case it has to how you tackle that type of problems that I have discussed in the previous class. So today I'm nothing to do more. I will do the same more questions related to this problems, that how will tackle the stereochemistry if in a molecule stereochemistry is mentioned. So let's see more questions. So in this type of questions here, for these questions I will do that. Here you see that lithium aluminum hydrides is there and stereochemistry is mentioned here. Okay, this is the stereochemistry is mentioned. So for this cyclohexanes, it is exist in the chair form. So first we will convert this in the chair form that we have discussed in the previous class. First convert this cyclohexanes in the chair form because this exists in the chair form. Okay, now name these groups, start naming it. Let's say if I name this 1, 2, 3 and 4. Okay, so at 1 and 4 some groups are there. So let's see this double bond OH. Let's say here we have this is 1 and 2 and 3 and 4. At the 4 this group is there. Okay, now thing is that whenever lithium aluminum hydrides or any reagents or any nucleophiles attacking to these groups, these carbonyl groups, and if it is a less bulky, then always prefer that do the axial attacks. Okay, so past preference will be the axial attack. Why? That I have discussed in the previous class. So now I will try to do the axial attack. So for axial attack, if there is any chances of 1,3 diaxial interactions, on that case axial attack is not possible. Okay, so we will check the axial attack. Is there any 1,3 diaxial interactions is present in any of the cases, then on that case we will not do the axial attack, we will simply do the equatorial attack if the reagents is less bulky. So here that reagents is H minus, so this is a less bulky, so we will look that is there any 1,3 diaxial interactions is there or not to do the axial attack. Okay, so 1,3 means 1, 2, 3. So here no groups at the axial. Okay, so in this side no axial attack is there, 1,3 diaxial interactions is not there. Now we will look from this sides 1, 2 and 3. So here also no any groups at the axial. Okay, so there is no 1,3 diaxial interaction, so we can do easily axial attack. So axial attack we will do. So this will do by from this, and this is going to be like this. These groups. So here we will have H, and here we will have that O minus, and it will be as it is. Okay. So this after hydrolysis, this will get OH. So this group again after doing this attack and after doing this all these reactions, again convert this into this original form. Okay, so now I again going to convert this into the original forms. So first name this 1, 2, 3 and 4. So again in cycle for cyclohexanes. Okay, now so at the 1 we have opposite, at the above we have that hydrogens. So hydrogens usually we will not mention, and OH is at the downside, so I will write like this OH. Okay, and at the 4 positions 1, 2, 3 and 4, at the 4 positions this group is there. Here also at the 4 positions is there, so simply mention that in the 4 positions. Okay, so this is the final answers for these questions. Okay, so if so what we have seen here, first convert into this chair form, after that do the reactions, and again after doing all these reactions, again convert into this original form. Okay, now for these questions here, that lithium aluminum tetrabutyl is given. So this is how it is lithium plus, and this is aluminum. So here instead of that hydrogens, what is there? Orthobutyl is there, so that butyl groups is there. So now what actually wants to say here, that this become a bulky groups. Previously we have that for lithium aluminum hydrides, we have that lithium aluminum, then we have that 4 hydrogens. But in this case what has come, that this butyl groups has come. It means that they wants to make it a bulky groups. So now that from here you are getting that H minus, but now from this here you will get that this minus. It means that it become a bulky group. So I have seen that, I have told that if a bulky groups is there, on that case it always attacks in a equatorial positions. It cannot attack in a axial positions. So here we will not look that whether one triaxial attractions is present or not, because our reagents now is become a bulky groups. On that case we always do through equatorial attack. Okay, so for that case we will do always equatorial attack. And one more thing, since it become a bulky groups, it will become a less reactive, and so if it is a less reactive, so it become a more selective. It means that as like here what we have seen here on this case, this S minus LiAlH bond is weak and unstable, and since it is also less bulky groups, so all these favors it to a very strong reducing agents. But now it become a bulky groups, and on the case this aluminiums and this carbon, this is the aluminum and carbon bonds, so this the size also become a little bit comparable, so it become a less reactive and more selective. Okay, so now we'll solve these questions. So for these questions, how we'll solve this? If this is the questions on this case, but now the reagent is lithium aluminums and butyl groups, so this become a bulky reagents. Okay, so now it will always do the equatorial attack. Okay, so first I will do this cyclohexanes in the chair form. So first I will convert into a chair form. After that at the one, it says here we have that these groups, and here have these groups. Okay, so now since it is a bulky group, so it will always attack in the equatorial attack. Okay, it will not do axial attack. So here we will there is no problem of where 1,3 diaxial interactions is present or not. So that type of problems is not for this case, because here we always do the equatorial attack. So equatorial attack means this, so it will be here, oxygen will be this sides, and in these sides we have these groups. Okay, and this is like this. So now after hydrolysis it become OH. Now convert it into that cyclohexanes form. So at the power positions, we have these carbonyl groups, and this 1, 2, 3, and 4 positions. This group is the solution. So this become at the 1 positions, the OH in the above side. OH is that above sides, and down sides we have this butyl. Okay, and now this is at the 4 positions, this group is there. Okay, so this is the answers for these questions. Okay, so if there is a bulky groups, it will do that equatorial attack, so that's with the below sides here. And here we see that for this case this OH is the below side, and this case we see that OH is the above side. So this way the stereochemistry, how for this reagent stereochemistry for OH is these sides, and stereochemistry for this reagent is in the above sides. Okay, in this way we can solve the problems if stereochemistry is mentioned in the molecules. So we will move on to the next questions. In these questions, what lithium aluminum hydride is there, so this is the less bulky groups again. So here we will look that whether a 1,3 diagonal interactions is present or not. So for that, first we will convert these cyclohexanes into the chair form. So name this 1, 2, 3, 4, 5, 6. So at one groups, let's say if I put here this oxygen and 1, 2, 3. So at 1, 2, 3. At these 3 positions we have the 2 methyl. So one is at axial and one is at equatorial. And after that at 4 and 5. At 5 also we have that methyl groups. Here stereochemistry has not mentioned, so I will always, if stereochemistry is not mentioned, always try to do in equatorial positions if it is a bulky group, so that there will be no 1,3 diagonal interactions. But we see that on the three carbon centers we have the 2 methyls. So in one carbon there is only 2 chances, either it is axial or equatorial. But here in the both the cases atoms are there, so one has to be equatorial, one has to be the axial. Okay, if even the stereochemistry is not mentioned on this case, but it given that 2 molecules are there. So in one carbon center 2 possibilities are there, one has to be at axial and one has to be equatorial. Okay, so if these are same, then we can do that one is at equatorial, one is at axial and one is at equatorial. Now we will attack these reagents, that is H minus here. So now for this is a less bulky group, so we will look that whether 1,3 diaxial interactions is present or not in this case. So here if you see that, so if like you see 1, 2, 3, at the third positions we have the 2 methyls, and this is a bulky groups. So if you change it any case, like here we see that 1, 2, 3 at 1,3 diagonal interactions is present here because this is a bulky group. So if it is attacked, then there is a 1,3 diagonal interactions, so we can do the axial attack. If you change this into a other form also, let's say I am changing this into other forms. Let's say I am taking these groups in, let's say here also if I take now, this become a 1 and 2 and 3. 1, 2, 3. At the 3 I have the 2 methyls, and at the 5, 3, 4 and 5 I have, let's say, this methyl. Still we see that 1, 2, 3 at 1,3 diagonal interactions is present, because here the 2 groups are already fulfilled. If one is there, then we can change that. If it is above, then we can make it down, so that axial interactions would not be happened. But here both are fulfilled, both the both axial and equatorial both are there. It means that we cannot change it to a equatorial position. So here if any groups at 1/3 positions, at third positions, if 2 groups are mentioned and 2 groups are bulky, okay, with respect to this, if at the third positions if 2 groups are there and both are bulky, on that case 1,3 diaxial interactions always present. Okay, so in this case we can't do axial attack, we have to do that equatorial attack. So we have to do here equatorial attack only. So this will attack through the equatorial. So this will be the equatorial attack. Now, okay. So this become O minus. After hydrolysis, it become OH, and we have that equatorial attack H here, and 1 2 3 here we have one is at axial methyl and one is at equatorial methyl, and 1 2 3 4 5 here also we have that methyl here. So now change this into a cyclohexanes form. Okay, so at 1 2 3 4 5 and 6, so at one positions we have that OH at the above sides, OH at the above sides. Okay, and H will not mention because H will everywhere there, so it's better not to mention the H. Okay, so 1 2 and 3, at 1 2 3 here we have that methyls here, because here stereochemistry is not mentioned, so make it as the same molecules, and at 5 we have the methyls. So this is the final answers for these questions. Now we will move on to the next questions. Okay, so for these questions, this is again a cyclohexanes, although here oxygen is there, but this is again a cyclohexane. So convert into cyclohexanes always exist in a chair form. So first convert into a chair form. So here let's say 1 2 3 4 5 and 6. So 1 2 3 1 2 3 4 5 and 6. So at one position we have, let's say, double bond is there, and at 2 and 3. So see again at 3 positions both are bulky groups are there. Okay, 3 positions both are bulky groups are there. Let's say one is methyl here and other is, let's say, here COO, let's say butyls, and 4 and 5 here let's say we have that methyl groups. So since at the third positions both are bulky groups are there, so there if you change in any forms 1,3 diaxial interactions must be present. So in this case we have to do a equatorial attack. Okay, so I will do a equatorial attack here also. So this O minus will go here. After hydrolysis it will get OH, and this is going to be that H minus H. Okay, and this is let's say CO, let's say butyl, and this is going to be methyl, and here also methyl is there. Okay, so now convert into this cyclohexanes form. Convert this into a cyclohexanes form. Okay, so now make this at O, we have that OH at the above sides, and the same things after that, this all will be same, so same things we will mention here. See here that at 4 positions oxygen is there. Okay, so mention that 2 3 at the 4 positions oxygen is there. Okay, so 1 2 1 2 3 4 here oxygen is there. Okay, and here we have that methyls in above, and down so we have this CO, that's butyls, and we have this methyl groups. Okay, so this is the final questions for this. This is the final answers for these questions. Now we will move to that next questions. I'll erase this. So for these questions, again here that nitrogen is there, but still it is a cyclohexane, so convert into a chair form. Convert it into a chair forms and name this 1 2 3 4 5 and 6. Note that I'm naming from here, we can name from anywhere, either here, anywhere. so that you have that more chances of to do no 1,3 diagonal interaction. So naming we do in such a way, or make this make the groups in such a way so that if any chances of 1,3 diagonal interactions, that should not be present. Okay, that's what that main regions of this naming and regions of this putting this molecule, so that 1,3 diagonal interactions, if any forms, if 1,3 diagonal interactions not there, that we will do. Okay, so main our intention is that so that 1,3 diagonal interactions should not be present. Okay, so here I like to put that here double bond over 1 and 2, here CH3 is there. So stereochemistry is not mentioned. So always if stereochemistry is not mentioned, then it is better to put that in equatorial positions, because this is a bulky groups. So stereochemistry is not mentioned, and if it is a bulky groups, then try to keep that molecules in a equatorial positions, because 1,3 diagonal interactions, so that not present in any cases. Okay, so since it is a bulky group, so I will put in a equatorial positions 1 2 3, and at 4 positions nitrogen is there, so mention that nitrogen is here. And here also we have that CH3. Since equatorial, since stereochemistry is not mentioned and CH3 is a bulky groups, so I will try to put this in a axial equatorial positions, and this lone pairs is there, that will be at the axial positions. Okay, so this is the we convert this cyclohexanes into the chair form. Now attack that H minus, because this is a less bulky groups. Now we will look that whether 1,3 diagonal interactions is present in any case or not. Okay, so see here 1 2 3, so now 1,3 diagonal interactions is there, and 1 2 3. So at 1 3 at 1 with respect to 1 third positions. Okay, with respect to 1 third positions, if is there, so we look that each any chances of happening 1,3 diagonal interactions or not. We will look only 3 positions with respect to this where we are going to attack. Okay, so now here at third positions, from here 1 2 and 3, at third positions no bulky groups are there, so no 1,3 diagonal interactions, so we will attack this in a axial attack. Okay, so this is going to be that here H, and here we will give that O minus, and after hydrolysis it get OH. Okay, after that these molecules remain as it is. So name this molecules will be same as it is there. So now after doing this, convert into this original questions form, because in the questions in this form is there. Okay, this form is not there in the question. So after doing this reactions, convert into this original form. Okay, so this here that OH is the downsides. Okay, and here it will be that CH3 will be there, and same things will be there here, nitrogen, here also CH3. Okay, so this is the final answers for these questions. So we will move to the next questions now. Do something. Okay, so for these questions, first what we will do that here also that 2 cyclohexanes is there, so we will convert these 2 cyclohexanes into chair form. Okay, and what we see that name this 1 2 3. So at third positions we have 1 2 3. Third positions we have this oxygen. Okay, and here hydrogen is there at above, that is at axial, and one hydrogen is there, that is below, also here axial. Okay, now we are attacking that lithium aluminum hydride, that means H minus. So now we will see that any 1,3 diagonal interactions is present or not. So here we see that with respect to 1, this is 1, let's say, this is 1, 2 and 3. So here hydrogen is there, so hydrogen is a less bulky group, so there is no problem of 1,3 diagonal interaction. So here we can do that, and here also you see 1, 2, 3. Here also no group is there, so here we can do that axial attack. Because at these groups, at these third positions, if CH3 or any bulky groups are there, on that times it have 1,3 diagonal interactions. But here that hydrogen is there, and hydrogen is a less bulky group, so there is no problem of 1,3 diagonal interactions. Sorry, there will be no 1,3 diagonal interactions, so you can do the axial attack. Okay, axial attack means this is from these sides and this is going to these sides. Okay, so this is going to be that OH is this sides, this is OH, okay, and this is H, and this is going to be the H here. So now if I write this into this original forms, so convert this, okay. So now whatever the same things we will mention here. So here that OH is the downside, so mention this OH in the downside. So this is the final question, final answers for these questions. Now we will move to the next questions. For these questions, how, since this is also that is cyclohexane, so we will convert this into a chair form. Okay, so here let's say 1, 2, 3, 4 and 5 and 6. Okay, so now this is 6, so here we see that it yes, so let's say this is okay, so 1, 2, 3, 4, 5 and 6. So at one positions we have these oxygen groups, and we have that at two positions at the above we have, and here also at the above we have, and that is here we have that C double bond, and here we have that N and this, and here we have that hydrogens. Okay, so this I have after converting into a chair form, this is that what this molecules is. Now what you will do, that lithium aluminum hydride is there, so reagent is H minus. Okay, so now this H minus, where it will attack. So now we know that this nitrogens is less electronegativity and oxygen is more electronegativity compared to the nitrogens. So which is more electronegativity, that pulls electrons, that attract electrons toward itself more strongly. So oxygen is a electronegative, more electronegativity group, so this lone pairs are more stronger bonds, where this lone pairs are more get attracted toward oxygen. So these are not so much easy to release, but here it is easy to release. But the problem is here, see that these lone pairs are involved in a resonance. So if these lone pairs already involved in the resonance, so, but here in this case these are not involved in any resonance, any conjugations, sorry, or this lone pair are involved in a conjugation. So these are not actually available, they are actually in a conjugations, but these are freely available. So although it is a more electronegativity groups, still this lone pair of oxygen will sorry, first what we will do, first we have that lithium aluminum hydrides. Lithium aluminum hydride means H minus is there. Okay, so for this H minus, what it will do, it will reduce this. Okay, So here in this case it is the amide, and in this case this is the aldehyde. So this H minus will first reduce these things. Okay, first what the work of this reagents. So this will reduce this. So if it will be this is all are in the above sides, and 1 2 3 1 3 diaxial interactions is there. So this will attack in a axial positions to this group. Okay, so this is OH and this is the H. Now in this case this CONH2 CONH, this is going to be converted into this amide groups also. If you give lithium aluminum hydrides, that is reduce this amide to a amine groups. So this is going to becomes CH2. Okay, this groups. Okay, now if you do this lithium aluminum hydrides, now you have this acetylenes, that is these groups. These groups. Now in this case here that this nitrogen is there, this oxygen is there. So now since this is not involved in any resonance, now this will attack to these groups, and this is going to like this, and this is going to be reduced like this. So the answer will be this group. So now this is going to be that CH2, and this is going to be that N, this, and this is going to be the COCH3, and this we have here above OH, and here we have that H. Okay, so I will solve more about of these questions. So now up to this, after that we can do more reactions also, it will happen. But now let it these questions here, because we are looking about the lithium aluminum hydrides now. So I will solve these questions more after discussing about more about of that other reagents. Okay, because some other concept also here I will solve later these questions. So for these questions, now if you look the same things here, you don't need to, this is stereochemistry is not there, because you see the stereochemistry is not mentioned. So simply that this is how these electrons are more available, so this will attack here. This is going to be like this, this is that. Okay, this is going to be this groups. This is the final answer for this question. Stereochemistry is not mentioned here, so we will not look the stereochemistry. Okay, so we will discuss more about of this type of questions after discussing more of the reagents. Now we will look at stereochemistry in acyclic molecules. So stereoselectivity in acyclic molecules. So before solving the questions related to stereochemistry in acyclic molecules, if any reagents is there, for that we should know the three models. Okay, for stereochemistry for acyclic molecules, we will discuss the three models is importance. Okay, so what are the three models? After these three models, we'll say that how the stereochemistry for acyclic molecules. The first model is that Cram's model. Cram's model. So for this Cram's model, what we have seen here, so if this is a groups, carbonyl groups, and to these alpha carbons, okay, to these alpha carbons, or you can write here, if this is a carbonyl groups, to these molecules, to these alpha positions, this is alpha, okay, here the stereochemistry is mentioned. If it says here any group is there in this alpha carbons, if stereochemistry is mentioned, let's say one is this sides, this is in the planar molecules, and let's say one is at that, let's say we have here H, and let's say here we have that CH3 groups. Now we are doing a lithium aluminum hydrates or any reagents, or we can do any reagents. Then on that case, what is the stereochemistry of this, what is the if this here H minus is attacked to this carbonyl groups, then in which side this H minus will attack? What is the stereochemistry of that H minus, of this H whenever it attack it? Okay, so for that case, what we see that we will study these Cram's models and all these other two models. Okay, so now for Cram's model, what it says, if your this groups is there at alpha positions, if stereochemistry is mentioned, now if any reagents you are attacking to this carbonyl groups, the attacking of these reagents in which side, that is given by a Cram's model. So what it says, that Cram's model says, if see that here in these molecules, first actually what you see, that divide these three molecules according to the size. So it has only one molecule and small molecule, so let's say it is a small groups, and this is that CH2 CH3, so this is a large molecule compared to this three, and this is a medium groups. Okay, so divide these three groups into a small, medium, and large. Okay, now what the Cram's model says, if large groups, so Cram's model is talk about of that large molecules, that is more interested about of large molecules. Cram's model means large molecule. Okay, so for if large molecules anti to this CO molecules, anti to CO, then this incoming reagents, then the reagent attack from the stereochemistry of small group sites. So then reagent attack from sorry, then stereochemistry of these incoming reagents will be the same stereochemistry as the small group site. Okay, then reagents attack from small group site, that is the same stereochemistry as a small group site. This is what says that Cram's model. This is the Cram's model. Cram's model is that that has to be acyclic molecules. For acyclic molecules, if large molecules is anti to this, here it is a seen if this large molecules, if these CO molecules anti to large molecules, then the reagents attack, that upcoming reagents will attack from the small group side. This is that Crumb's model. Or this also alternate way, what it says that if large group seen to these carbonyl groups, then the reagents attack from medium group side. This is the alternative way. Either you remember this, or also you can remember this. Both are the Crumb's model. So Crumb's model also say that if large groups is seen to CO groups, then reagents attack from the medium group sides. So here we see that this is the carbonyl molecules, and to this carbonyl molecules, this large is seen, because this and this is in the syn. So if it is syn, then attack this incoming reagents from the medium group sides, means from the above side. Okay. So if that questions is there, let's say the same questions I am solving here. Okay, so now here this is groups. Sorry, if we have here H and here you have that CS3, on that case, if that lithium aluminum hydride is there, that is going to be H minus. So this H minus will attack. So what you see that here to this carbonyl groups, this is syn. Okay, so for that, whether it is syn or anti, what will do that convert into this form. This is CO and this is H, and now this is like this and this is H, so convert into here H, and here it is CS3. So now this is syn to these groups. So if it is syn, then this hydrogens will attack, this reagents will attack from that medium group side, that is this. So their answers will be, so this is attack from the medium group side, means this is above side. So H will be the above sides, and this OH will going to be the downside, because if it is H side, then other will be that OH side, because already one is plane. And the same things will be remain as it is. This is the answers for these questions. So in this way we can solve that. Here that this is syn, okay, to this carbonyl group, so attack from that medium group side, that CS3, that is in the above side. So this H will be in the above side and this will be at the below sides, because if it is going to be above side, then definitely this will go to the below sides. Okay, now this is about of this Crumb's model. Now we will look that Crumb's select model or anti-Crumb's model, and after that we will look that comfort model. After discussing all these three models, we will discuss the questions answers to clear more about of these models. Okay, or to solve this type of questions. So now we will look that second models. The second model is Crumb's select model, or this also called that anti-Crumb's model. What this model says that if that same things, if a carbonyl groups is there, to that at the alpha positions, okay, if at the alpha positions, if stereochemistry is mentioned, let's say this is this groups, and here we have, let's say here we have any OH, or here we have, let's say, any Z, and here we have that H. Okay, so now what we look that, so first our work is to do this is large and this is small and this is medium. Our work is to first make it large and medium. We'll divide it. Now what we look that, this is at alpha position, so we have these three groups. And what is Z? That Z has to be any groups that has at least one unshared lone pair. This Z, that should be that type of atoms or that type of groups that has to be at least one unshared lone pairs. Okay, at least one unshared lone pair. Like if we have that oxygen case, so here that unshared lone pairs are two are there. Like that Z is like if it is OH, or it may be, let's say, OR, or let's say it may be O minus, or maybe it is SR, or it may be S minus, any type of groups which if it has an unshared lone pair. Here also at least one unshared lone pairs. Okay, it should have at least one unshared lone pair. For that case, it may be this, and it may be any groups, like if it is NH2, NR2, here one unshared lone pair is there. So any group if it has one unshared lone pair, on that case this Crumb's model is applicable. So that Z, that should have at least one unshared lone pairs, and with that, this is the one conditions, and with that the second conditions, that whatever you are giving that reagents, in this reagents that metal is there, let's say lithium aluminum hydride. In this case metal is lithium plus. So this type of metals, whatever you are giving this reagent, the metal should have chelating properties. Okay, so which metals have this chelating properties? The metals like lithium plus, magnesium 2 plus, cesium 2 plus, and titanium 4 plus, copper 2 plus, and lithium, magnesium, cesium, titanium, copper, and Zn2 plus, like that metals. Okay, if this type of metals are there, then it will this metal show the chelating properties. So the metal should have chelating properties, and the examples like this type of metals. Okay, and if metal is Na plus or K plus, I can write here, if metal having no chelating properties, metals like Na plus and K plus, on that case Crumb's chelate model not applied. Okay, on that case simply applied that Crumb's model. So if the metals having no chelating properties, like if that sodium and potassium, this type of metals are there, then on that case Crumb's chelate model is not applicable. On that time simply apply that Crumb's model. Okay, so if these two conditions are satisfied, like first conditions is that metals that if that Z, in this Z groups, it should have at least one unshared lone pairs, and secondly metal should have chelating properties, like this type of metals are there. On that, if these two conditions are satisfied, on that case apply that Crumb's chelate model. Now these groups here, examples like this reagents, like we have that lithium aluminum hydride. On that case, metal is lithium and it shows the chelating properties. And if Z is in the Z, at least one unsaid lone pair is there. On that case, apply that Cram's chelate model, or we can say that MgOH2. This type of reagents are there. On that times, apply the chelate models. And if that like the reagent is an LiAlH4, on that times not use that Cram's chelate model, because this Na will not show the chelating properties. Okay, so now we will look that what this chelate model says. This Cram's chelate model says. So this Cram's chelate model says that if these two conditions first has to be satisfied, after that we will apply this Cram's chelate model. That model says that if chelating group means if Z, or I can write here, if Z is here, we will in this Cram's chelate model, here we will look about of this Z with respect to Z, okay. And in case of Cram's model, we do that with respect to large groups, okay. So with respect to Z, if Z is that is seen, if Z is seen to CO groups, if Z is seen to CO groups, then attack will be from small group sites. Okay, so this is that Cram's chelate model. What it says that if Z is seen to the CO groups, then attack will be from the small group site. So this has to be the seen to these groups, then we will attack this lithium aluminum hydrates that is from the small group side, means this in the back sides. Okay, like if that example is there, like if we have these groups, let's say here we have, here let's say we have here OH, and here we have, let's say NaH. Now we are giving that lithium aluminum hydride. So now we will look that all the conditions of Cram's chelate model is applicable here or not. So first, that metal should be that that show the chelating properties. So lithium here, so lithium show chelating properties. Okay, so this is the first condition, and second condition is that this Z groups has to be one unsaid lone pair. So unsaid lone pair is there. So we will use here that Cram's chelate model, not Cram's model. Okay. So now divide this into three groups. This is smaller, this is medium, and this is the large. And this is the chelating groups. Okay. So now that we will look that this Z has to be that seen to these groups. Okay. So now what we will know, in the questions it is mentioned that this is in the left side, but actually what you see that you have studied this in stereochemistry, this type of groups always in the right side. Okay, so this is actually, okay, so this is actually at the this side OH, and this is actually this side. Okay, now if I simplify this, then how it is COH and this. Okay, so this H is this and OH is like this, because this is right side. Okay, so I mentioned this in the right side. Now I want this into a seen to this groups. I want to make this in a seen to this group. So seen means you see that this is there. So this is seen to this group. So I want these groups into this side. So for that, what I'll do there here, simply move this to here, and this is there and this is here. After rotating it, rotate here, this to here and this to here. Okay. So now this is going to be like this and this. So now this OH will be this side and this H will be, so this group will be this side and H is going to be this side. So now this is seen to this carbonyl groups. Now attack this H minus, that lithium aluminum hydrides, from the small group side. So small group side is in which direction? Small group side, that is at the back sides. So attack this, attack from the back sides. So this is going to be C and H is going to be the back sides and this is going to be the front side. After that, make this the same or original forms whatever it is given. So this is going to be the same forms, because in the questions this will be like this, in the same form that will be there. And OH is this sides. Okay, it means that after doing this reagent attack, make this into the original forms whatever it is given in the questions, the same form we will make it. Okay, so this is the final answers for this type of question. So in this is the what says that Kram's-Stillet model. So Kram's-Stillet model says that if alpha carbons of with respect to carbonyl groups, if Z group is there and that Z group is such that atoms or group that should have at least one unsaid lone pairs. Okay, this is the first condition. And second condition is that the metals is given, not the reagents. In that reagent the metal is present, that metal has to be show the chelating properties like lithium and magnesium, zinc, cobalt, selenium, all these things. But if that metal is like sodiums and potassiums, that type of metal is there, on that times Kram's model is not applicable. On that time simply do that Kram's model. Okay, so this is what the Kram's-Stillet model says. It will be more clear if you discuss the questions. Now we will look at next model, that is Conforth model. The third model we have, that is Conforth model. Actually this is just extended of Kram's-Stillet model. What it says that the Conforth model, that if Z, if chlorine is there, so in that time I have seen that I have written that OH, I have written that NH2 or NH2 or that I have written, but I have not written that chlorine. Why? See, chlorine also have that unsaid lone pair. It has 3 unsaid lone pair, but still I not mentions, because this chlorine, what says that if chlorine is there, or chlorine or any halogens, okay, any halogen, on that kind it has that 3 unsaid lone pairs, and due to these 3 unsaid lone pairs there will be the repulsions, and due to these repulsions what happened that this Z molecules always try to go anti to this carbonyl groups. Okay, so this Kram's-Stillet model, on that case if Z is chlorine, on that case it will not apply uh, anti-Kram's model or Kram's-Stillet model due to the repulsions present in the chlorine if halogen is present. So even if the conditions of all Kram's-Stillet models satisfied, then also we will not use Kram's-Stillet model if chlorine is present. On that time for chlorine we will use a specific model that is called the Conforth model. Okay. So if it is a chlorine, on that times we will use a Conforth model. What that Conforth model says, let's say if a carbonyl groups and to this alpha positions, let's say here we have H and let's say we have this chlorine or any halogens, let's say any halogens, XH halogens like Cl and Br iodines, any halogens is there on that times, if that reagents are lithium aluminum hydrates, that metal shows that chelating properties, on that times we will not use that Kramp-Stillet model, but we will use that comfort model. But that comfort model says that here we'll make, here this is specific to halogens. If so, first we will divide into this is large, this is small, and this is medium. So if halogen is anti, so this will be never be to the same, because if this halogen is seen to this your group, repulsions will happen. So this X will comes always anti to this group. So if halogen is anti to this carbonyl groups, then reagents, that incoming reagents attack from small group side. So this what the comfort model says. Comfort model says that this halogens has to be anti to this carbonyl groups, and then the reagents will attack from the small group sides. Okay, so it means that if this is the questions here, now make this to the anti. Okay, this is CO, here it will be H, and so now this H, see that this H will be here and this X will be here, but I want this X in the sint anti to this. So what I will do, that I will make this little bit here, and this is a little bit here, this is a little bit here, so that this will be the anti to this group. So this CO H and this X will be here and H will be here, and here this groups 2, 1, 2. Okay, so or like this. Okay, so now after that attack this lithium aluminum hydrates, that is H minus, from that small group sides. So small group side is that is in the back side, so attack this reagent from the back sides. So that will be going to be that. So H will be the back sides, that reagent attack back side. So this OH will go to the above sides. Okay, this is X and this is going to be the X. So now after doing this, convert into this original forms, whatever there in the questions, in this form. Okay, that is going to be this H, this is going to be OH, this is going to be H, and here the same questions, here X is that side, X, and this is the final questions for this. If the questions is this is the final answers for this question, this is the final answers for these questions. Okay, so in this way we will tackle the problems if stereochemistry is mentioned in acyclic molecules. In that time I will use these 3 models, that is one is Kram's model, anti-Kram's model or Chillet models, Kramp-Stillet models, and then comfort model. And this comfort model is specifically for this halogen case. Okay, so this is the same as Kramp-Stillet model, but instead of that OH and H, if halogen group is there, on that times we will use the one-part model, we will not use that Cramp-Stillett model. Okay. Yes, obviously here also there should be that the unsaid lone pair should be there. Okay. So this is about of these three models. Now we will solve this examples related to these models to clear more. Okay, so now we will solve these questions. So we will see these questions here. This is the COH groups and this is methyl lithyl. Lithium lithyl. So this is Li group is there, and you see that here NBN is there. Okay. So here lone pair is unsaid lone pair is there, but the problem is that BN2 is there. That is BN means benzyl. So this is actually B. This is actually CH2 N groups, and here again we have the CH2 this vinyl groups. So due to this bulky groups presence adjacent to it, this becomes so bulky that this reagents not able to do the interaction. So due to this bulky groups, this lone pair will be not able to do that, not able to chelate with this lithiums. Actually what this Li plus will comes here and that will do the chelations, but this lone pair due to this bulky groups it will be not able to chelate with lithium. So here we will use a simply Cramps model, not Cramp-Stillett model, because if the bulky groups is there, then that lone pair is not able to do the chelations. Okay, so if bulky groups are there, and on that case due to steric hindrance, this lone pair not able to chelate with these metals. So on that times we will not use that Cramp-Stillett model, we will use simply a Cramps model, even if it satisfies all the conditions of Cramp-Stillett model. Okay, so now here we will do simply a Cramps model. So first look these questions. So these questions now here that actually this is given in the right side, but this back side will be always in the right side. So they in the questions they want to make confuse. So this is there, we will make simply into the right, because that we have studied that is always this type of back side is always in the left side. Okay, so here H, here we have that methyl, and this will be always in the back, because this back side will be always in the left and this will be always in the right. Okay, so this is actual, because they want to make confuse, that's why they write this in the right side, but this type of back group will be always in the left side. So we will do first convert into that what is actually it is. So make that. After that what we will do, we will make that small, large and medium. So this is small, this is medium, and this is large. So how we will make which is small, medium and large? According to that atomic numbers and that we have studied in stereochemistry, which is large, which is small, and the same concept. Okay, so this is H, so small groups, and this is methyl, this is medium, and this is the large. So now what that here lone pair is there although, but this is not able to do chelate. So here Cramps model you will see. So what the Cramps model says, Cramps model says that Cramps model is interested with the large groups. So this large group should be the anti then attack from the small group side, and if a large group is seen to the this carbonyl groups, then attack this from the medium group side. So what we will see, so in these three models we see that we'll just make it. So Cramps model, what the Cramps model says that here Cramps model is interested of large. So first that is anti, we will always remember in a scene wise, because anti it may be sometimes complicated. So always do crumbs model large compared to scene. Okay, large scene to this carbonyl groups, then attack will be from that medium group side. Medium group side. This what the crumbs model says, and crumbs select model, after satisfying all the two conditions, that is one that at least one unsaid lone pair should be there, Z, and that metal should be so chelate property, and if these two conditions satisfied, then what it says that here interested with the chelate groups, syn 2. Okay, both here also syn 2 carbonyl, then here attack from that small group sides, small group side. This is attacking. Attacking reagents. Okay, this is what they say that crumbs chelate model, and what that comfort model says that halogen groups. Okay, halogen group here that anti, because this is due to the lone pair repulsions, this halogen always go to anti to carbonyl groups, then attack from again the small group side. This is the whole about of this three models for acyclic molecules. Okay, for acyclic molecules, these three models we will do. One is Crumbs model, another is Crumbs chelate model, another is Comfort model. Okay, so we can remember that. Here we can remember this in a simple way, that syn anti. Okay, and for this we will see that first medium, and we will say that small, and we will say that small. So we can remember like this: syn anti, then medium, small. Okay, and this is for Crumbs, and this is for anti Crumbs, and this is for Comfort. The syn to carbonyl and syn to carbonyl and anti to carbonyls, then attack will be medium, small. So this way we can remember to solve that if stereochemistry mentioned in acyclic molecules. For that case, we use these three models to solve that stereochemistry type of questions. Okay. Now, so this is a Crumbs model. So what the syn, then attack from the medium group side. Okay. So first we will change into a this small, large, and medium. So it is interested with that large groups. Crumbs means large. Okay, so this will has to be the syn to this carbonyl groups. So for that, what we will do here, this will be the methyl, and this is H, and this is NBN2. Okay, so now I want this large groups. This is the large groups. So this one I want to be to the syn. So what I'll do that, just move it to this. This is here to here. So if you move it, then okay. So here we have that NBN2, and here we will have that methyl, and here we have that hydrogens. So now attack this from the small group sides. Okay, so from small group sides, so small group is now in which side? Look here, this hydrogens is okay. So after if in the previous I mentioned anything wrong, first this is the actual correct, but you see that here you look that here this hydrogen is now in which side? This is in the left side. Left side means this is in this is this is left means that is this back side, and right means this. Okay, so this that incoming reagents will attack from this small group side. So sorry, medium group side. So medium group is this, so this attack will be in the above side. Okay, this is C, here H, so attack will be that medium group sides, because this is medium and this is in the above, so here will be the H, and OH will be this side. That is carbonyls, and H will be this sides, and OH is this sides, and after that this will be okay. So after that make it into that what it is exact the same things. This okay, after that we will make the same things methyl and whatever there in the questions. That is here H, here NBN2. Okay, this is the final answers for these questions. Okay, so likewise I think we will solve the next class these questions. We'll make all these questions, we will solve all these questions in the next class. Today after this, thank you.